So, how can you imagine more than 10% of effort will be paid for the design review, only design review, not for code review, but design review. I'm not sure how much effort do you pay for the design review. I'm not sure, but this is a real Japanese IT project data. But of course, most of the data are around here, appeared around here. So only less than 1% effort for design review against the total effort of the project. Anyway, so according to the data, so and the y-axis represents a post-release defect density. So and we investigated almost 100 data, valid data. Then, so we find more than 6% of the design review effort project. For that project, so all of the project the post-release defects for that project is all of the project is 0. Okay? So which means there's no defect detected during the operation. If the project more than 7% of design review effort compared to against the total effort. But when I look at around this lab area, so less than 2% of design review effort ratio. So those projects has a wide variance about the post-release defect density. So for example, over there, so 0.5, 0.25. So you might remember, so the median of our data for the post-release defect density is 0.01. So it's wide variety we have. So according to this chart, we can learn. So paying much review effort will contribute to the higher level of post-release defect, the lower level of post-release defect density. So, but of course it depends on the quality, like a strategy for the organizations. So some organizations can afford to pay such a lot of effort for only for design review, but some are not. So it depends on, but at least so the data shows a lot of design review effort will contribute to a lower level of post-release defects. And also review effort density. So which means how much effort do the project pay? Did the project pay for the review, including design review and code review, and person hours per kilosource lines of code. Okay. And by dividing the values of this matrix at the median, so the higher group, high density of review effort contributes to a higher ratio of review defect detection. So the y-axis represents the matrix I previously explained, the number of defects detected during review against the total number of defects during the project. Okay. And let me explain somewhat detail about why we change the matrix. So here, design review effort ratio, and here, review effort density. What's the difference between these two metrics? Okay. This matrix can be used during the project. So you can measure your size of your project when the coding was finished, and you can count the number of review defects when you finish your review phase. Then you can get the value of this metric. However, design review effort ratio, this metric can be measured just after the finish of the project. Okay? So we can measure this metrics only when the project was finished. So we can collect a total effort and we can collect a design review effort. But again, so this review effort density metric can be used during the project. So you can estimate or predict the project project status or the reliability or review defect detection ratio by using this metric. So we can predict this kind of measurements. And also, let me look at the relationship between review defect detection density and the design document density. Okay. So the x-axis represents the design document density. So which means the number of pages of design document per kilo source lines of code. So for example, so we have 1,000 kilo lines of code of product, and we have, for example, 100 pages with a design document. Then the measure represents 10. Okay. So the median with the measurement is almost 16. By dividing the median into two, by dividing the values at the median and into two groups, and the y-axis represents the design review defect density, so which I explained in the previous slide. Then, so the relationship, by investigating the relationship, the higher density of the design document contributes to higher density of design review defect detection. So this kind of relationship we can see from our empirical data. But again, but the number of data is relatively small. So, but I mentioned before, so we have more than 4,000 project data, but most of them are invalid to analyze, to make an analysis for this perspective. And also, so this is a final chart about the review. So when I take design document density on x-axis, and when I take a design review defect density on the y-axis, and take a logarithm, so there's a positive relationship between these two metrics. So which means higher density of the design document. So for example, 10-page document or 100-page document or 1,000-page documents. So it means a large number of design document pages will contribute to the higher density of design review defect detection. So which means if you have only a very small pages of the design document, so we can't find a lot of defects during design review. But if there is a rich documented design specifications, we can detect a lot of defects during the design review phase. So the relationship, again, so by connecting these individual relationships, so to achieve the higher reliability in terms of the post-release defect density, we need to increase the ratio of review defect detection, so which means the number of defects detected during review against the number of defects, the number of total defects detected during the project. And to increase this, so we needed to pay enough effort for review, as well as a lot of defects detected during review phase. And to increase the number of defects detected during review, we need to write enough volume of design documents. So this kind of relationship investigated. Okay.
Know about it. They didn't go and do it on purpose because Rob Saab is bad. They did it because they were naive. Because they're in marketing, or they're in sales, or they're in business. They don't know what software engineering needs to do things. So very often, the pain points we encounter are ways to improve. And I like to say that testing in the dark, almost every strategy in here came from real problems that were painful, that had to be solved. And if they didn't get solved, people would lose jobs. It wasn't just we didn't find the bug. It was that the company would go bankrupt or would lose $1 million. This is serious, life-threatening even. Serious stuff. So it's important to try to learn from your pain. The testing in the dark is a metaphor. It's a metaphor. It's not a real thing. It's a metaphor. Metaphors are always wrong. They're useful, but wrong. So they're just models. Models. Wrong models. When we see testing in the dark, it's a metaphor for saying we have no information. When we say seeing the light, it's a metaphor for saying the information is becoming clear to us. But unfortunately, seeing the light doesn't mean you solve the problem. It sometimes means just before you die, you know, I'm dying. It's sort of, you just know just in time that you should have quit. Many people say software testing is about being the headlights of a car. So think of the metaphor, the headlights of a car. But you're not driving in a clear weather, you're driving in a fog. I don't know if you have fogs in Malaysia. I know you have a lot of rain here, but fog, something that we see in Canada in the mountains, fog. And you're driving through the fog, and sort of your lights are just showing you a little bit as you're guiding, and you get to see just enough of the road to navigate. And sometimes what I like at testing is that's what we're doing, is we're the headlights of a car, and we're waiting for the fog to lift. Another thing we do in engineering is reconnaissance. So I'm going to show you a little bit about recon, how to do some reconnaissance work. As testing is about learning, in my experience. Testing is about learning. Testing is not about truth. Testing is about knowledge and sharing knowledge. What we do with it, that's business. Sometimes that has to do with truth. So also a little bit about instrumentation, not too much in this class, but sometimes if we are blind, we can navigate with instruments. I personally, twice, navigated a ship. This is the ship. That's me. That's the Furbeck. Furbeck. At the time, it was the largest registered ship in Canada. And you know what they put on that ship? Titanium ore. And do you know what you make with titanium ore? It's boring. White paint. White paint. Quebec is one of the largest producers of titanium ore in the world. Who cares, right? It's like there's a big market for white paint. But when I was on that ship, we're going on the St. Lawrence River. St. Lawrence River is 160 miles across. That's 300 kilometers across one river. 300 kilometers across. And when we're driving that road, the fog is so dense, you can see nothing. They put me in the navigation. I have this captain's thing, the steering of the ship. I was there, it was me, no one else, just me. And I could see nothing. But I could see everything. Because they had sonar, radar, echo sound systems, redundant controls, satellite stuff. They had so many ways to see even though we were blind. And by the way, when you steer a ship like that, just to make a little move, you have to do it so many miles in advance that it was impossible for me to fail. Because I was there for 5 minutes and then he said, okay, go away, Rob. Don't crash the ship. When you're working on a project, someone is asking you to test. Do you test for fun? Maybe you're testing for fun. This is not a course for testing for fun. If you're testing a project, it's because someone asked you to do it. And that person probably has a reason. If you have no documents, no requirements, you can still learn from them. Why are you asking me to do it? Who matters? Who are you testing for? Who's paying for the product? Who's paying for the development? Who's paying for the testing? Who's developing the software? These matter. So if you have hardly any, you're doing this project for a reason. And I will give you example after example of dramatic differences in testing for the same exact technical project, but with a different purpose, a different reason for it. So why are we testing? Why did we develop the software? Why? What also matters? What is we're actually testing? Are we testing the hardware? Are we testing the software? Are we testing the integration of the systems? Are we testing the utility of the systems? What problem are we solving? And if we're testing and we're trying to learn, what type of issues are we concerned with? What is a bug? What's a bug look like? If your job is to look for a bug, you might want to study a little bit of what type of bugs matter. Even if you don't have a requirement document, you can talk to your stakeholder and say what type of problems matter and learn from them what type of problems to look for. It's interesting to know what is good enough too. Quality. I will not define quality. I have no customer in the world who cares what my opinion of quality is. When they hire Rob Sabre to help test, they don't do it because of my definition of quality. And I have pretty high standards of quality, and for me, quality's got to be fun and entertaining and enjoying. It's not just a black and white measure. That's my personal view. But what I do is I learn what my stakeholders feel quality is. And then when I'm testing, I try to help give them information about their view of quality, not about my view of quality. So one of the problems I see a lot of testers do is they try to impose a view of quality on a project. And then they find problems, but they're not the problems the stakeholders care about. And you get so caught up in your view of quality that you lose sight of the customers. So I'm concerned about quality. Learn what quality means to your stakeholders. What does it mean? I have identified over 15 different views of quality. I've identified over 15, and I'm still finding more. It breaks down to 3 major categories. One category, conformance to requirements. That's from Phil Crosby. Software conforms to requirements. Does that matter to you? Some people, that's important, right? Some people, it isn't important. Well, if it's important, then your job is to hunt for requirements. Your job is to hunt for them, because almost every project I work on, even if you think you have requirements, you only have requirements about a little bit of information, about the delta, about what's changed. You don't have all the requirements. The good requirements are actually hidden in the walls of the buildings. And they ooze out of the history of the organization. There's slime coming out of the walls, just like in the movie Ghostbusters. Slime! And that slime is called an implicit requirement. And implicit requirements are things we have to hunt down. My favorite implicit requirement is, if I back up the data last week, I have to be able to restore it next week. Have you ever seen that written down? I've never seen it written down, but I've never seen a system with persistent data that didn't have that requirement. It's always there. I always test for it. It's always important, but it's never written down. So if you're people like following ISTQB definitions and all this stuff, quality conformance requirements, then we have to hunt for the requirements. Quality could also be suitability to purpose. This is Joseph Duran. Quality is suiting purpose. It doesn't matter that you conform to requirements. Who cares about requirements? Chuck them in the garbage, they're a distraction. Quality is suitability to purpose. That's Joseph Duran, wrote the Quality Control Handbook in 1950, pioneer in quality systems. Pioneer. And he said conformance to requirements is bogus. It is misleading and detrimental. Quality, he said, is suitability to purpose. Almost every agile discipline today uses that type of definition for quality. It's not, does it conform to the requirement? Can the user do something useful with it? Is it practical and useful for the user? And you're asking the question, ask not what the software does for the user, but ask what the user does with the software. It's a totally different, if you have the same project and you test it with conformance to requirements, or the same project and you test it with suitability purpose, you will have dramatically different test cases, test procedures, test data. Dramatically different bugs. Dramatically different. So I don't care which view is it. I'm not saying there's good or bad or right or wrong. It's not judgment. It's different though. So learn what quality means. The last one is more modern. It's like a bunch of hippies in San Francisco. Quality is delivering value to stakeholders.